So good afternoon, everyone. My name is Alban Farchi, and today my topic will be efficiency and consistency of the covariance localization in the ENKF. So I will first start with a few reminders about the Kalman filter. So I will be talking about the analysis step of the Kalman filter, which is summarized by these three equations, which you all know. And in the ENKF, the assumption is that the statistics are determined by the properties of the ensemble, sample mean and sample covariance matrix. The problem with this assumption is that the true background error covariance matrix can be full rank, whereas the rank of the sample covariance matrix is limited by the ensemble size. And indeed, we observed when the ensemble size is too small that the sample covariance matrix is characterized by large sampling errors, which often take the form of spurious correlations at long distance. And a common solution to this is to use localization. So either make the analysis local or use a localized sample covariance matrix. The first method is called domain localization. It relies on a collection of local analyses, which are by construction and by definition embarrassingly parallel. But for this method, we only have a ad hoc treatment of non-local observations. The second method is called covariance localization. It relies on the show product, but for this method, we do not have an obvious parallelization of the perturbation update. However, we do have a rigorous treatment of non-local observation, which is why this method is interesting. So, in this presentation, I will be interested in implementing covariance localization in the deterministic ENKF, and in particular in the local ensemble square root filter, for which the perturbation update can be summarized by these two equations. So first, we use the localization matrix ρ in order to localize the sample covariance matrix. And then we use this B matrix in order to compute and apply a left transform update to the anomaly matrix X. So we will have two topics. A first topic dedicated to how to efficiently implement these two equations. And a second topic will be how to will be the consistency of this equation. And by consistency, we mean how well does the analysis sample covariance matrix match the exact analysis error covariance matrix. So let's go to the first topic, how to implement covariance localization in an efficient way. And in order to do this, we choose to use an augmented ensemble. So during the analysis step, and during the analysis step only, we choose to use an augmented ensemble. We compute more perturbations, and the perturbations should be constructed in such a way that they have the correct sample covariance matrix. So in order to compute this augmented set of perturbations, we propose two different methods, which I will detail right now. So we have modulation method and truncated SVD method. So the modulation method is based on a prior Cholesky factorization of the localization matrix here. And then you just have to compute a modulation product between the Cholesky factor and the ensemble anomalies. The modulation product is defined element-wise by this equation. And as you can see, it is a mix between a show product for the state variable index n and a tensor product for the ensemble or mode indices I and j. This modulation product is based on a factorization property which has been shown by Lorenz in 2003, and it is already used for covariance localization, including in operational centers. A key idea with this method is that if the localization matrix is static in time, then we can pre-compute the Cholesky factorization And the resulting method is very fast because you only have to compute this element-wise product. The second approach, the truncated SVD method, is a bit more direct. In this method, we compute a truncated SVD of the localized sample covariance matrix, and we use this truncated SVD in order to form the augmented ensemble. The point is, since we are using localization, the B matrix will be sparse, and therefore we will be able to use efficient and parallelizable method in order to compute the truncated SVD. And for example, in our numerical illustrations, we will use a random SVD algorithm derived by ALCO, and for which we already had some presentation. But the principle of the random SVD is quite simple. You just apply the B matrix to random vectors in order to find the dominant singular values and singular vectors. The main advantages for this method is we have beautiful theorem. We prove the convergence of this method. So now that we have our augmented ensemble, we need to perform the perturbation updates, and we need to obtain an updated ensemble which has the correct ensemble size. And how are we going to do that? The solution is to use the augmented ensemble in order to compute an approximate left transform of the original ensemble. So we start from the exact left transform. We replace the B matrix by the sample covariance matrix of the augmented ensemble. And then with a bit of linear algebra, we can show that the second equation is equivalent to the third equation, where now the linear algebra is performed in the augmented ensemble space, which means that the matrices are smaller. This formula has been derived by Bokeh in 2016 and has been later used by Bishop under the name gain form of the ETKF. So this is the update formula we are going to use in our numerical illustration. So now we are ready, and we want to test this approach. In order to do this, we will use the Lorenz 96 model, which is given by this set of differential equations. We use a pretty standard configuration where everything is observed. We use 400 variables. The ensemble size is set to only 10 members, which means that localization will be necessary. And we will look at the root mean square error between the truth and the analysis. So on the left plot, you have the evolution of the RMSE as a function of the augmented ensemble size. In blue, you have the truncated SVD method. In red, the modulation method. And for comparison, the green horizontal line is the RMSE for the LETKF algorithm. So as you can see, both methods yield similar scores at some point as the LETKF. However, the modulation method required a larger augmented ensemble size in order to yield similar scores as the truncated SVD method. However, before we jump to conclusion, we must take into account the fact that the modulation method is a bit faster, which is why on the right we plotted the wall clock time as a function of the RMSE score. So you have in red the modulation method, and in blue truncated SVD method with and without parallelization. And now you can clearly see that for a given level of RMSE score, the truncated SVD method is faster. So we want now to provide a second test series for which we want to test satellite observations. So in order to do this, we introduce a multi-layer extension for the Lorenz 96 model. So this multi-layer extension consists of 32 coupled layers of the original model with 40 variables. You recognize here the first line, which is the original Lorenz 96 equation. And you have here two coupling terms between adjacent layers, one coupling from below, one coupling from above. And last point, we will take a forcing term linearly decreasing from 8 at the bottom layer to 4 at the top layer. For this model, we will use satellite observation. So we suppose that each physical column will be independently observed using 8 satellite channels plotted here with different colors. Apart from that, the setting is very similar to the original Lorenz 96 setting, and we will use an ensemble of only 8 members, which means that again localization will be mandatory. And finally, since we are performing observation column-wise, we can use domain localization just like in the LTKF in the horizontal direction. And therefore, our covariance localization method will be used only on the vertical direction. So here are the results. You have the evolution of the RMSC score as a function of the horizontal localization radius. In green, the LTKF algorithm. In blue, you have the truncated SVD method for an augmented ensemble size of 8 members and 64 members. And the modulation method, augmented ensemble size is equal to 8 members and 128 members. So now you see that using this augmented ensemble approach, you can yield much better RMSC scores than the LTKF, which is obviously not a surprise because we are using non-local observations. And we still have the conclusion from the previous test series is that the modulation method requires a larger augmented ensemble size to yield similar scores at the truncated SVD method. So here 128 compared to 64. However, in this configuration, both methods can benefit from the parallelization of the local analysis, and therefore the truncated SVD method is not always the fastest approach. So to conclude this first study, we have shown how to implement covariance localization in the Ensemble square root filter. The analysis is performed using the augmented ensemble approach. 2 methods have been proposed to compute the augmented ensemble, modulation and truncated SVD method. The methods have been compared using the Lorenz 96 model and the multi-layer extension. And we conclude that both methods are suited to the assimilation of satellite observations in a spatially extended model. And now we arrive to the second topic of my presentation, which is dedicated to the consistency of the perturbation update. So here I recall the perturbation update. First, localize the sample covariance, and then use the B matrix in order to compute and apply the left transform update. For this update, the consistency relationship is this one. What does it mean? It means do the analysis ensemble have the correct sample covariance matrix? In other words, is the sample covariance matrix of the analysis ensemble equal to the analysis error covariance matrix computed using the Kalman gain? And here, a first source of inconsistency lies in the fact that the B matrix is not equal to the forecast sample covariance matrix. And we must now think, how are we going to fix this inconsistency? And we propose a different approach. Instead of looking for an analysis ensemble such that XA, XAT is equal to PA, which is our previous consistency relationship, we think that it could be more consistent with how the perturbations are defined to look for an analysis ensemble such that the localized analysis sample covariances are equal to the analysis error covariance matrix. So if we follow this approach, the perturbation update becomes in three steps. First, use the localization matrix to regularize the B matrix. Then compute the exact analysis error covariance matrix. And then, finally, solve this minimization problem to find the analysis ensemble. And obviously, with this minimization problem, we don't require an accuracy for the long-range covariances, which is why we can hope to find a better accuracy for the short-range covariances. A few words about this minimization problem. It is similar to a weighted low-rank approximation problem, and therefore we expect that there is no tractable solution for this problem. Contrary to the non-weighted case, for which we have the Eckart-Jung theorem. However, we can compute analytically the gradient of the cost function, and it is given by this equation. And therefore, we will be able to compute a local solution by using an iterative gradient-based minimization method. And that's what we will do in the numerical illustration section. In order to test this new approach, we use the Lorenz 96 model. The exact same configuration as before. Everything is observed, but we use this time 40 variable, so the standard configuration. And we will vary the ensemble size, and we will look at the evolution of the RMSE as a function of the ensemble size. So we compare three different algorithms. First, the LETKF. Second, in red, the local ensemble square root filter, the one that uses the exact left transform update. And third, we use the modified local ensemble square root filter, the one which uses the new perturbation update we just defined. So if you look at the RMSE score, you see that using the new perturbation update results in a systematic improvement in the scores. Improvement lies between 3 and 6%. So we are in the Lorenz 96 model, very well-tuned configuration. So 3 to 6% improvement in RMSE score can be considered quite significant. On the right plot, we have the optimal multiplicative inflation factor as a function of the ensemble size, again for all three methods. And then what is really striking is that the modified method, the new method, requires much less inflation than both the original local ensemble square root filter and the LETKF. And in order to further study these points, we looked at the evolution of the RMSE as a function of the multiplicative inflation factor at a fixed ensemble size. So for example, here you have 8 members and 16 members. Again, all three algorithms. And now we see that indeed using the new perturbation method in green, the need for inflation is reduced. You need less inflation, and you can even perform very good without inflation in the case where the inflation factor is exactly 1. And we think thus, that this this performance results from a better consistency of the perturbation update. So indeed, we are able to better represent the analysis error covariance matrix using this new method. So to conclude about this second topic, we have defined a new perturbation update method for the local ensemble squared filter. For this method, we look for an analysis ensemble such that the localized analysis error covariance matrix, the localized sample covariance matrix of the analysis ensemble are equal to the analysis error covariance matrix. We found, using numerical illustration, that the new method yields systematic improvement in RMSE scores, and the requirement for multiplicative inflation has been much weakened. These advantages of the new method have been confirmed using sparse and infrequent configuration for the Lorenz 96 model, as well as using the Kuramato-Shepaczynski model. And finally, we concluded that the new perturbation update is indeed more consistent in the sense that it allows to better represent the analysis error covariance matrix. So, thank you for your attention, and I welcome any question. And if you want to read our paper, you're welcome.
We have time for some questions. Peter, Jan.
Sorry about me again. So two questions. So in your SVD method, right? You
yes.
Randomized SVD method that you use. Can you show again how exactly you do that?
Here.
Yeah. Sorry, the truncated SVD. That's what I mean, right? So
yes.
So which.
So you compute a truncated SVD of the B method. So you write.
But you cannot calculate that in any realistic system, right? You cannot calculate that.
Yes, you can, because you can use the random SVD algorithm, which only requires to be able to apply B to any vector.
But how would you do that in this case? Because you only have X.
It's not about, it was about computing B or not.
No. So I don't want to calculate B. I know I want to calculate B times something, but.
So you want to calculate B applied to a vector?
Yeah.
So B is equal to rho short product with xxt applied to vector V, and using you can decompose that and show using the columns of X that it is equal to XA short product with rho applied to XA short product with V.
Okay.
So this is a pretty standard decomposition, which you can. It's straightforward to show it, and it can be used to compute this. You only require to apply the localization matrix, and if you suppose, for example, that you have invariance in translation, then you can apply it in Fourier space, and it's straightforward.
Okay, that's how you do it. So, and that B matrix, of course, if you look at the spectrum of the B matrix, I would expect it to be not very steep.
So it depends on your problem.
Yeah, but
yes.
But I guess for many, so for your Lorenz 96 problem,
yes.
If you have let's say a relatively narrow diagonal banded B matrix, then I guess that the spectrum is quite.
So the more thin the diagonal, the less steep is the
exactly.
descent.
So
yes.
So in this case, so your randomized SVD will not be very efficient. That's of course what I'm trying to do.
The randomized SVD can be efficient if you use some numerical tricks by ALCO. But the thing is that you require you need a larger augmented ensemble size if you want a fixed precision for your approximation.
You can multiply several times the B matrix so that you have the power of the spectrum. So it has a cost. It makes the spectrum.
Oh, okay. But then that. Oh, okay. Yeah.
So in fact, what you do is you compute the SVD of BBT to the power Q, B times BBT to the power Q, for some Q equal, let's say, 1 or 10. So this is harder to compute, but in the end it converges better.
So, but then you just use the power method more or less, right? Yeah. Yeah. But still you.
Q is 1, 2, 3.
Yeah, that's okay. I need to think. Thanks.
Other questions? Here.
So thanks for your very nice talk. Do you see anything that will prevent your scheme to be applied to the case of interest where you have a hybrid B, linear combination of localized ensemble as well as static covariance matrix?
I don't see anything that prevents from applying this, but it just requires a few more mathematical developments. But
so you think you will apply the truncated SVD to this hybrid B, or do something separate for the climatological B and the localized ensemble B? Or
I'm not sure what the best approach would be in this case, but if you can apply the full B to any vector, then you can directly apply this approach.
Yes.
If this is not possible, then we will have to think otherwise. But is this possible in your case, or in the case you have in mind, or?
It is.
So
we do that in iterative schemes. Thanks.
Other questions? Okay. If there are no other questions, then we have a longer break. So we'll have coffee until 4 o'clock, and we'll thank Alban one more time.